Okay, here's the next talk, binary search tree of permutation.
Well, thank you for the introduction. So this is a work in collaboration with Benoît Corsini and my advisor, Valentin Ferret. And this is about binary search trees that I will call BSTs now. And when you study BSTs, you need an input, which can be a permutation or a random permutation. So a question you may ask is, what kind of random permutation should you consider? And the model we chose to study is something called permuton samples. So I'll try to define and motivate this model, and then to present one of the main results we could prove on the height of such BSTs. Okay, so I guess you all know what a binary search tree is. So when you go to the left subtree, the labels decrease, while if you go to the right subtree, the labels increase. And I'll just consider the simplest type of BST there is. So no self-balancing or funny stuff. Basically, when you have just a sequence of numbers, the first number is going to be the root of the BST. And then when you insert a new number, then you compare it with the root to decide whether to go to the left or to the right. And you keep doing that recursively. Okay, so with this sequence of numbers, for example, you get this BST, which has a height of 3. And this is the main thing I'm interested in. Now, notice that the values here are between 0 and 1. That will be natural in what follows. And now, if you're only interested in the height of the tree, then you don't really need to know the exact values. So you can replace the lowest value with a 1, the second lowest with a 2, and so on. You get a permutation, seen as a sequence of numbers. And the BST of this permutation has the same shape as the actual BST. So it will be useful to have these 2 point of views. Now, if you want to study the BST of random permutations, what kind of random permutation should you consider? And the model we chose to study is related to the theory of permutons. So I won't go into the details of permuton theory. The only thing you need to know is that a permuton formally is a probability measure, on the unit square, where both marginals are uniform. So it means that if you use a permuton to sample a random point on the unit square, then the x coordinate will be uniform between 0 and 1, and the y coordinate will also be uniform between 0 and 1. But the two of them will be correlated in some sense. So for example, the Lebesgue measure on the unit square is a permuton. It's the simplest one. Now you can also find permutons with nice smooth density with respect to the Lebesgue measure, like the one on the left. And you can also find permutons with no density, like the one on the right. And these two permutons will have very different properties. And here I'm rather interested in the permutons that look like the density on the left. Now that's just the formal definition of a permuton, and you may wonder why that's an interesting definition. And the thing is, in permuton theory, it makes sense to say that a sequence of permutations converges to some limit permuton. So it's a bit analogous to the theory of graphons, and you can think of a permuton as a limit permutation. For instance, the one on the left here, it's not just any permuton, it's actually the limit permuton of Mallow's random permutations. Okay, so that's a permuton, and you can, if you have a permuton, you can use it to define random permutations. To do so, suppose you have a point set in the plane. So you can read it from left to right. That is, you can order it by increasing x coordinate. When you do that, you get a sequence of points, which gives you a sequence of y coordinates. And if you replace the lowest y coordinate with a 1, the second lowest with a 2, and so on, you get a permutation. For example, if you have this point set, you read it from left to right. The first point you read is this one. So the y coordinate is 0.3. Then you read 0.6, then 0.1, 0.8, 0.5, and 0.7. And when you do this operation, you get this permutation, which has the same relative orders as the sequence of y coordinates. Okay, so that's just a deterministic construction. If you have a point set, you can use it to define a permutation. If you want a random permutation now, you need a random point set. And an easy way to do so is, if you have a permuton mu, you can use it to sample IID random points, and that's going to be the random point set. And then the random permutation defined from this random point set is what we call a permuton sample. or we may say that it's sampled from the permuton mu. Okay, so that's our model of random permutations. For instance, if the permuton is the Dubach measure, it's quite easy to prove that this random permutation is uniformly random. And that's a first interesting feat with this model, is that it's a continuous deformation of the uniform distribution on permutations. So the idea is that if you have a permuton which has a nice density with respect to the Dubach measure, then you may think that this random permutation is quite close in some sense to a uniformly random permutation, which is quite a common thing when you study random permutations. For example, it's the case for Mallow's random permutations. But here, the parameter is a permuton mu. It's not just a real number. So this defines an infinite dimensional family of random permutations. And this is quite nice because we have a unified way to study all of them with this geometric approach. And we can prove very general things for permuton samples, which gives us results for a very wide family of random permutations. And also, in some sense, you may justify that informally, this family of random permutations are dense in some sense in the whole family of random permutations. And also, this is also informal, but studying this sequence of random permutations, it gives us some insight on the link between asymptotic properties of random permutations and properties of the limit permuton, because this sequence of permutations, it converges to this permuton mu. And so the idea is that if you go back to this permuton here, so as I said, it's the limit permuton of Mallow's random permutations. Now, you can use this permuton to sample random permutations. These random permutations will not be Mallow's distributed, but we have good reason to believe that they have very similar properties as Mallow's random permutations. So studying permuton samples, it can give us a lot of insights on other types of random permutations. Okay, so that's the random permutation I want to use as an input for the study of BSTs. Yes? Yes. Yes, that's a very good question. I forgot to say, there's a parameter Q, and to have a limit permuton, which is very nice like this, Q needs to be something like 1 minus beta over n. And the density here depends on beta. So it's when the parameter goes to 1 as n goes to infinity with a well-chosen speed. And yes, this one is just for 1 beta. I could not tell you which one, but one of them.
Just to the parameterization 1 is the uniform distribution.
Yes, absolutely. The Mallow's distribution will appear later in the talk for a reminder. Yes, absolutely. Okay, before, where was I? Right, there's one shortcut we can do before studying the BSTs of permuton samples, is that their BSTs can actually directly be constructed from the point set. Indeed, suppose you have a point set, as before, you read it from left to right by increasing x coordinate. Well, you can study the BST of the sequence of y coordinates. So if you have a point set, you can define on the one hand a permutation and on the other hand a BST. And the BST of the point set will have the same shape as the BST of the permutation, because the BST of the point process here depends on the sequence of y coordinates, which has the same relative orders as the permutation. So it's not very exciting like that, but it will be useful to have these 2 point of views where the BST of permuton samples can be directly studied from the point set. And from the point set, well, the root of the BST is going to be the leftmost point. And then you know that each point above here will be on the right subtree, and each point below will be on the left subtree. So it's very easy to construct directly just by looking at the point set to construct the BST, just rotated by 90 degrees. Okay, so now for the results. the thing we want to study on these BSTs is the height, because it determines the complexity of basic operations. So a general question is, given a random permutation, what can be said about the height of its BST? Now, in general, not much. It can go from logarithmic to linear. So now a better question is, what kind of assumptions do you need on the law of the random permutation to have a logarithmic depth for the BST? Okay, well, the first case to study is the uniform case. And Luc could famously prove that for uniformly random permutations, the height of the BST behaves as some constant C star times log n, where the constant C star is defined by some implicit equation. Now, let's look at some other random permutations. For example, the famous Mallows distribution, which is a Gibbs distribution. So you have a parameter Q. Here we can assume that it's between 0 and 1. And the Mallows distribution gives a mass proportional to Q to the power the number of inversions of the permutation. So as it was said, when Q is close to 1, then this distribution is close to the uniform distribution. And when Q is close to 0, then this gets concentrated around the identity permutation. And for this distribution, Luigi Dario-Berri and Benoît Corsini could prove that if Q is close enough to 1 in this precise sense, then we have the same asymptotic equivalent for the height of the BST. Okay. Now, Benoît Corsini also studied another Gibbs distribution, which is not biased by the number of inversions, but by the number of records. So it's called the record bias distribution. And he could also prove that for some range of parameters, we have the same asymptotic equivalent for the height of the BST. Now, could we hope to, sorry, yes? Oh, a record is a value in the permutation which is higher than all previous values. It's a left to right maximum here. Okay, so now could we hope to have a result in a similar flavor for permuton samples? So remember that when the permuton is the Lebesgue distribution, then the permutation is uniformly random. So we could hope to have a result stating that if the permuton is in some sense close enough to the Lebesgue measure, then we have the same asymptotic equivalence here. And it's the case. Now, suppose you have a permuton. You're going to make two assumptions on it. The first one is that the permuton has a density on the unit square, which is bounded. And the second one is that the density close enough to the left edge of the square is continuous and positive. If you make these two assumptions, then the height of the BST is also equivalent to C star log n. So what does it look like? Well, this is the unit square. On the right, on all of the unit square, there's a density which is bounded, so it's at least a bit nice. And close to the left edge is positive and continuous, so it's very nice. And what happens is that when you sample random points using the permuton, some of those points will appear on the left band here. These points in the construction of the BST, they will define the first generations of the tree. So that's what we call the top tree. And we want to have a very nice density so that this top tree is quite close to the BST of a uniform permutation. And these points will be evenly spaced and have nice properties. But then we also sample points on the rest of the square. And these points, they will define a sequence of subtrees that will be attached to some points of the hanging trees. So we call them the hanging trees. They will be attached to some points of the top tree. So we call them the hanging trees. And it would be a problem to have very deep hanging trees. It could modify the result about the height in the end. So we need at least some assumption on the density. And we chose to assume that the density was bounded there. Okay, so it may help also to look at some examples. Okay, we don't really see the color here, but here you should imagine that there's a left band here. So the permuton on the left, it has some uniform mass on some band on the left, and also some uniform mass on some line here. Okay, so it does satisfy the second assumption because there's a continuous and positive density close to the left edge, but it does not satisfy the first assumption. There's not a density on the right. Well, for this permuton, what happens is that the top tree is going to be the BST of a uniform permutation. So it's very nice. It will have a logarithmic height, but then the hanging trees will all be long branches. And you can prove that one of them is a bit too long, and it will modify the constant before the logarithm. So it's actually a general fact that if you have only the second assumption about the density on the left, then the height will be logarithmic, but you might not have the right constant, as it's the case here. And the other permuton, you should imagine some diagonal band here, going from, okay, you have the diagonal here, and you have also another super diagonal here. There's a uniform mass on this, and also there's a small triangle here where there's a uniform mass. Anyway, that's a permuton. And when you study this permuton, it satisfies the first assumption because there's a bounded density. It's a density which is constant on some subset. But the density is not continuous and positive on the left edge because it vanishes here. And what happens for this permuton is that quite a lot of points will be sampled close to this diagonal line. And these points, they will all appear on the rightmost branch of the BST. So in the end, you can prove that the height of the BST will be at least a constant times square root of n. So it's not even logarithmic anymore without the second assumption. Okay, so these two assumptions, they make sense. Now, why, more precisely, why does it work? Well, as I said, the idea is to decompose the BST as a top tree on the left and a bunch of hanging trees on the right. When you do that, you can bound the height of the BST between the height of the top tree and the height of the top tree plus 1 plus the worst height of hanging trees. So if we want to prove our theorem, we can proceed in 2 steps. The first one being to prove that the top tree has the right height, and the second one being that the hanging trees all have negligible heights. Okay, so let's focus on the first step. Well, as I said, the density close to the left edge is continuous and positive. So it's very nice. And we would like to compare the top tree with the BST of a uniform permutation. So we would like to do some coupling techniques. Basically, we would like to look at the point set, the random point set we have, take out a few points here and there, add a few points here and there, and get the BST of a uniform permutation. The problem is that BSTs, the height of the BST of a point set is not monotonous with respect to the point set. With this example, you can see that it's possible to take out a single point and to double the height. So it's not a nice thing because when we modify point sets by taking out a few points here and there, it may completely modify the height. But what saves us is that if you look at these 3 points here, they're on the same branch on the left, and they're still on the same branch on the right. So that's what we want to use. More precisely, define a chain in the tree as a subset of vertices which are all on the same branch of the tree. If you use this definition, then we have a lemma stating that if you have 2 point sets, P minus included in P plus, and if you have a chain in P plus, and you look at the points of the chain which remain in P minus, then these points, they will form a chain in P minus. So it's not possible to destroy, in some sense, a chain by just taking out points. And if you apply this with a chain of maximal size in the BST, well, a chain of maximal size, the maximal size of a chain is just the height of the tree. So if you apply this with such a chain, you deduce that the height of P minus is at least the height of P plus minus the number of points that we lost, the number of points of the chain that disappeared when going from P plus to P minus. So in some sense, we were able to reverse this inclusion into this inequality, but we have a term here which may be a problem. Now, the way we want to apply this is that later we will have a point set P, the one we're interested in. We'll bound it between 2 point sets P minus and P plus, and we can apply this lemma twice to each inclusion, to deduce this chain of inequalities, bounding the height of the BST between the height of P plus and the height of P minus with some error terms. And now the question is, can we make these error terms small enough? So let's just recap. We have a permuton mu. It has a density rho, which is very nice, close to the left edge. It's continuous and positive, so in particular, it's bounded above and below by two constants. Now, the first step is to actually study Poisson point processes instead of the current point processes we have, because Poisson point processes are very nice. So this is something we will have to deal with later. But for now, let's just suppose you have Poisson point processes with an intensity n times rho. Then the nice thing is that we have a thinning property, which allows us to take out a few points randomly here and there to get a smaller point process, which is homogeneous. It means that the points inside of this smaller point process are uniformly distributed. And it's also possible to add a few points here and there to get a larger point process P plus, which is a homogeneous Poisson point process. When you do that, P minus and P plus contain uniformly distributed points, so their BSTs are the BSTs of uniformly random permutations, and it's a good thing because we know what their heights should be, and we can use the previous lemma to deduce a sequence of inequalities for the height of P, of the BST of P. And then, well, the problem is at the beginning, we did not have Poisson point processes, so we need to apply depoissonization techniques, which are a bit technical, so let's not talk about them. But now, let's go back to this inequality for the height of the BST of P. The problem is we had some error terms, so can we make them small? Well, if we just do that, they won't be small. They will be not negligible. And the one refinement we need is that for now, we use the fact that if the density is constant, then the sampled permutation is uniformly random. But the thing is, if the density is a function of x times a function of y, then the random permutation is also uniform. And we can also apply the previous result for the height of the BST. So now, the only thing we need to refine in the previous argument is to say that if we have a density rho close to the left edge, then it's not only bounded above and below, but it can be made very close to a function that only depends on y. And when you do that, well, you can bound rho between two functions that only depend on y, and then you do the exact same thing as before, except P minus and P plus are not homogeneous, but their density are functions of y. And we can still apply the uniform result for them. And when you do that, you can make the estimates good. Okay, so that's just for the height of the top tree. And well, if you want to prove the result for the height of the whole tree, you still need to study the hanging trees. So let me just explain in 2 words why it works. Well, to understand the heights of the hanging trees, you need to understand the sizes of the hanging trees. And let me just spoil the last slide. So we have this figure. The sizes of the hanging trees, they depend on the width of the horizontal bands here. And the width of these horizontal bands, they are defined by the vertical gaps of the points on the left. So we need to understand these vertical gaps. But the thing is, you can prove that some of those vertical gaps will be of order log n divided by n. And actually not just one, but quite a lot of them will be of order log n divided by n. So the sizes of the corresponding BSTs, hanging trees, will be of order log n. And we need to show that their depth, their height, is negligible in comparison with log n. The problem is the density there is not as nice as before. It's not continuous and positive. It's just bounded. So we can't really apply the previous reasoning with the previous coupling. And instead, what we can do is to compare the height of a BST with the longest monotone subsequences of the permutation, which is not an optimal thing to do. But the nice thing is that longest monotone subsequences, they behave very nicely with respect to point sets and taking out points. So we have nice coupling for longest monotone subsequences. We can apply deviation estimates for them, and we can prove under the the assumption that the density is bounded, that all hanging trees have sublogarithmic heights. And well, when you do that, you deduce the result for the height of the whole tree. And now let me just mention one other result. The theorem about the height of the BST, it states that under sufficient assumptions, the BST of permuton samples has the same height as the BST of a uniform permutation. But it does not mean that these two BSTs look the same. For example, if you look at the BST of a uniform permutation, then the left subtree of the root has a random size, the right subtree also has a random size, and the two of them have the same distribution. It's not the case for permuton samples, and you can explicitly compute, this is called subtree size convergence, you can explicitly compute the distribution of the distribution of the size of any given subtree in the BST of a permuton sample. And that's all I wanted to say.
Time for two questions, Luke.
Yeah. Is there a chance of characterizing all the densities F to which you have height order log?
It seems a very difficult question in general. So
Do you expect a easy question from me?
the answer is we tried, but without these kinds of assumptions, we can't really say much about the BSTs, but it's obviously a future direction that we would like to tackle.
Fanta, why are you sitting so high? You too? Okay, Fanta, you only have to go up once.
Okay, so this is related to Luke's question, a little bit more precise. You assume that you have, as we're seeing picture here, positive continuous density close to the left edge. Do you really, why do you need it to be continuous? From your sketch here, I understand that you want it to be positive with a strict, constant lower bound in such a strip. But
well, we don't want just a lower bound. We want to justify that the density close enough to the left edge is very close to a density that only depends on y.
okay,
So that's the refinement we needed in the proof.
So you need that in the proof also, yes.
Yes.
Mm-hmm. And you have no guess if you really need that or not, I guess, after your previous answer.
Well, if the density is just positive, I think you can prove that it's still logarithmic in the end, but I think you may not have the right constants sometimes.
Okay, thanks.
Do you know, or do you at least expect universality for other tree statistics such as total path length or the shape functional behavior? That sort of thing?
I think the global ones, the global statistics, yes, we might expect some universality results, but it's still a very open question.
Okay, let's thank the speaker.